So today we'll continue with another demo on the How to E series of Litmus. So today we will describe how to perform FIO based benchmarking of your storage with Litmus. So let's go through the steps or the agenda that we'll follow as part of this demo. Clone the Litmus repo, set up the service account role binding for Litmus, create a config map for the kubectl, update the Litmus job with our FIO requirements, then run. So I'll be following these steps. I've already cloned the repo. So I'm going to go and apply the RBAC YAML. Okay, so the RBAC for Litmus has been set up. The next step is to create config map with the kubectl of the cluster. So note that I am running this demo on a GKE 3-node cluster, Kubernetes version 1.10.2. So I have the kubectl available in an admin.conf file, which I have placed in my home directory. So I'm going to go ahead and create this. And it is going to be restricted to the namespace Litmus. Okay, the config map has been created. The next step is to actually update the Litmus job. So let us go into the Litmus folder structure again. So this is the Litmus job. Now, a couple of values that I'll have to change for this cluster. What is the node on which I need to run my FIO, where my disks are located, where the preferred disks. We are doing this test on a standard SSDs. So I'm going to select the node on which the test has to be done and change the node selector. What is the FIO profile that I'm going to run? Let me run a simple basic read-write test on the SSDs, and we will compare the sizes. I'm going to set smaller size. And one more value that is of interest is the storage class. I'm going to go with OpenEBS upfront. So with this, we are done with all the first 4 steps. Now we are going to run the Litmus job. Okay, let's watch what is happening. So we have a Litmus pod that has already been created, and that has in turn launched the FIO pod. So the FIO pod application is basically a job that runs with OpenEBS standard storage class, and it has created a volume with a single replica. Now, As you can see, the FIO pod has actually started running the test. And we could actually take the logs and see what is the workload that is actually going to run. So we are going to run a basic read-write test, a simple FIO profile. And this is going to take a bit of time, where it is actually going to create the file, seed it first, and then run the workload. We'll repeat the same procedure with local PV, and then we will compare the numbers. Okay, so while this is running, we just very quickly went through the steps and even performed them. Are there any questions?
No, Karthik, I think we're good.
Okay. So as you can see, the FIO job has completed. And just to keep track, let us go ahead and see what the numbers look like. So we have used a standard SSD of 10 gig. And we've used a very small sized file size. So we're actually going to get a pretty high number with respect to our IOPS and throughput. So I'm just going to keep track of it in any case, though this is more a demo about how these tests are going to be run, or rather how they can be run, rather than actually doing a real benchmark. So I have taken down two values. So there is a read value IOPS that I'm taking, and then there is a write IOPS value that I'm taking. So the FIO output is in the JSON format. Okay, so let's see what has happened to our pods. So the Litmus pod continues to run. It actually does some background jobs on collecting the logs of the system, the kubelet logs, as well as the cluster info, and collates them and basically creates a zip file out of all these logs. So that can actually be seen on this node. So I have the node opened here, and MNT is the location where the logs are going to be stored. So all these logs, the playbook run logs, which internally is called by Litmus, is present in the hosts directory, and the pod logs and the cluster info is present here. So the system log generation, getting the kubelet logs actually takes a little bit of time. So basically, I will be more interested in looking at how the numbers look like on the local PV. So instead of waiting for that, I'm going to close this and go to the next test. I'm going to actually kill this job and go to the next test. I'll probably even clean up the PVC, but that's not necessary, so I'll just let that be. So this is terminating. So what we can work, the next step would be to actually change the storage class in our job and run the same test with the local PV. I'm going to keep the FIO parameters as is. And I'm just changing the provider storage class in the job. and I'm going to go ahead and create it. So there's a new Litmus pod that is actually getting created. Ignore the PVC control and replica pods from the previous test. We did not allow it to clean up. So we'll have another instance of the FIO job that is running, this time on the local PV, which will be launched by the Litmus pod once it comes into running state. So this time the Litmus pod has been scheduled on a new node, and probably took a little bit of time to actually create it. Okay, so this was pretty quick. So let me go and look at the completed pods. Okay. I'm going to see if the local PV was actually engaged. So it has not been. So the previous cleanup job or whatever we've killed has been incomplete. So let me go ahead and redo this step. Let me confirm that it is actually gone. Okay. We'll probably wait for a couple of seconds to actually let it go complete. Okay, it's taking a little more. Then probably go ahead and create the new job. Okay, the FIO pod is actually now running, this time on the local PV. I want to look at what values it is going to give me. Okay, so you can notice that the local PV has been created on this node, the one which I have just opened. The data is getting created here. Go back to the screen to see the results when they arrive. And you can also see that the local PV has actually been engaged. It's bound now. So we have got the numbers. I'm going to collect it once again. The same can also be found from the logs. So here I've got values for local PV. So this is the right. I'm going to record it. and here it is going to be for the read. Okay, so what we actually got was the read. Now I'm going to get the write. So pretty similar values, but that's probably because we have got a very small sample size to work with. Most of the reads must be available from the memory, though we can see that the local PV is slightly more when it comes to both writes and reads. Okay, that's all we have. So this is how you can benchmark your different storage backends with the Litmus FIO job.
Thank you, Karthik. We'll switch to the next demo.
Okay, thank you. I'll stop sharing my screen.
I will give a quick demo of manager disk detection.
Shobhan, can you please a little bit louder? I think you're...
Am I audible now?
Yes.
Okay. So I will give one brief demo of node disk manager disk detection. I have created one cluster in GKE with 2 nodes, and I will attach some disk in node and run node disk manager on that cluster, and I'll show the disk was attached disk was detected by node disk manager, and CRB related to that disk was created in ETCT. So I will run node disk manager OML here. So we are using OpenEBS node disk manager CI image to give the demo. This is my node 1, and one disk, that is OS disk, which is attached to that node, and this is node 2. In node 2 also OS disk is attached, and you can see the serial number, model, and the name of the disk here. Now I will attach some disk with node in node 1 and node 2 and run node disk manager on that cluster. So I have attached 2 disks in each node. If I do a lsblk with that node, then you can see demo disk 1 and demo disk 2 is attached with the node which is ending with 5p65, and demo disk 3 and 4 which is attached in the node ended with G2MW. Now I will apply NDM operator.yml. As NDM is running, as I demonstrated, you can see in my both node NDM is up and running. I will show the custom resource. Here, disk.openebs.io is the custom resource for the disk, which is used by NDM. If I do a kubectl get disk, then you can see I have attached two disks in each node, and one disk is the boot disk. So for each node, boot disk serial number is same. So we are getting one CR for the boot disk and 2 CR for the two different disks. So we are getting 5 resource of the disk. So you can see here this is the boot disk, and these are the two disks which are attached to the node. I will describe this resource. Yeah. So you can see this disk is attached with the node ended with 5p65, and the serial number is demo disk 1. So if I go here, demo disk 1 is attached with 5p65 with the node ended with 5p65. And the capacity is here 10 gigs. I do let's be okay. Then you can see that this capacity is 10 gigs. Now I will describe another resource, and the capacity is 12 gigs here, and the name is demo disk 2. Now you can see this is for this SDC, and the capacity is 12 gigs, and this is connected with the node 5 ended with 5p65. I will describe another resource from another node. So you can see here the host name is ended with G2MW, and you can see here and sorry, the disk name is demo disk 4, and here you can see demo disk 4 is attached with the node ended with G2MW, and here the name is SDC. If I do ALSBLK, then you can see the size of the disk is 17 gigs, and here the size is 17 gigs. Yeah, that's all for the demo. Any questions?
Apart from the
Thank you, Sean. We'll go to the next one.
the disk CR has information about the disk label and size. And
Yes.
are we going to add some other details also to this, or this is the final set of information that we are going to do for
No,
it?
this is not the final set of information. We will put some smart attribute, also some other details, also some event related to the disk.
Oh, okay, that answers my question.
So this schema is like you can see U1 schema. We can change the schema of the disk.
So today I'm going to demo CITF, which is a Common Integration Test Framework. This demo is prepared by Abhishek, Akash, Sagar, and me, and I'll be mostly okay. So yeah, let's move ahead. So what is CITF? CITF is nothing but a test framework which helps developer to write the integration test seamlessly, and developer don't have to worry about the environment setups and steps required to install the application. Okay, and the main purpose of CITF is to reduce the time required for for developer to bring up the setup and bring down the setup. In addition to that, CITF also provides some common APIs related to the Kubernetes and system utilities. Okay. So CITF in general. So what do we have in CITF is, in CITF you can specify your environment, like which environment you want to, bring up, and so which environment you want to bring up, and you can specify the platform basically. It can be a Minikube, it can be a GKE, it can be a AWS, but currently only Minikube is supported, and there are like other utilities, as I said. So how do we configure the CITF? But before this, I want to tell you like where CITF comes into picture. We have the integration test. Okay, so let's say the developer adds some change, some new additions to the application. For example, Node Disk Manager, we have added something new, and we just want to write an integration test for the NDM. So for integration test, as we all know, like we can use the BDD style libraries such as Gingo or Godog. So we are using Gingo mostly. But what about running those tests? Okay, developer might want to run those tests on Minikube or maybe on GKE. So by the help of CITF, and once CITF is configured for the integration test suite, developer can just execute the test using Go test, and Go test on the with the command itself, like only with the Go test, whole platform will come up, whole Kubernetes cluster will come up, and integration test will be executed. So to configure the CITF, we have like several parameters. Okay, first one is environment variable. We can pass the what kind of a platform you want. It can be a Minikube or GKE. So you can pass it using the uh, environment variable, or you can even write a configuration file which is like configuration.yaml, and you can just say like environment and I want the Minikube. Okay, or otherwise CITF assumes that if nothing is specified, it will just pick up the default, and that's it. So it will bring up the Minikube. Okay, so I'll quickly just demonstrate the how we have written the like how one can write integration test for the NDM. Okay, so here I have the NDM source code with me. Okay, so this is not checked in as per the CITF 8, but yeah, I can still demo you. So you can see that we just have to import the CITF library in your integration test package from where you write the test, and you just have to once you import the package, you have to create a global variable for a CITF instance, and you can instantiate the CITF in the BPO suite. We want Minikube and Kubernetes cluster to be up before executing the suite, because applications such as NDM runs inside the Kubernetes cluster, and we want to do integration test in the Kubernetes cluster. So that is why we have to start the Minikube plus all the instantiate all the platform related things, including the Kubernetes, in the before suite section. So we have written the CITF instance and created a new CITF instance. This, as you can see, that a new CITF instance can be created and can be provided with a configuration file path, the one which I just talked about. That configuration path can have it can have a file path, and that file can have the configuration such as environment and what kind of a platform you want, like Minikube or GKE. Here I'm not specifying any path, so it will choose the defaults because I don't have the environment variable set to. So it will just choose the Minikube, and we can just bring up the Minikube. If any error occurs in the CITF framework, that will be reported using the GoOmega. That will be validated using the GoOmega and will be reported using the register file handler of Ginkgo. Okay. So for every application we will need certain default utilities, such as for NDM we have some utilities written, and this will be the common things which developer will have to write once for their application. Okay, so next thing is after suite. So in after suite we will just clean everything whatever we had created, and the main integration test start from here, where we have to just give headings such as integration test. Let me go to the slides. So integration test for NDM you can see here. So the whole purpose of integration test, writing integration test, is like to validate the change, like whether it is perfectly matching to the all the requirements. And let's say some outside person comes and he came to know that this so and so support has been added to the NDM, but he wanted to confirm. So he can just go to the integration test and just see like in the form of statements that okay, these things are there. Okay, so this is the one kind of a purpose for the integration test, and that is what like that is how whenever a developer thinks about the integration test using BDD style, so they have to think in this manner only, like where what should be given and when it should be given, and what it should return. So these 3 lines we have to provide always. Yep. So like here you can see that our main suite name is like integration test, and when it should do. So what do we do is, like, when we check the log, it should show that it has started controller in the log. Okay, so for that we are, developer just have to call the internal APIs of the application, and which actually provides me the output such as this. Okay, so and once that is done, so you just have to match it with the Go Omega matchers, and if there is any error, so that will be handled by the Gingo only. Okay, so this is the one test. Second one is also there, where we are, NDM device list command is there. So we are executing that, and we are also executing LSBLK, and we are just matching the output of both. Okay, so I'll just quickly show you like how you can run this test. So it is like pretty simple the way we run the Go test, right? So once I say like Go test -v and test name, so test suite has started. Okay, so you can see that cluster is not up, and we'll start the machine. So this is coming from the CITF, and it will automatically bring up the CIT Minikube using CITF. Also, one thing I forgot to tell you that we can actually, in this util, let's say there are some methods where we can set the means user can set the image name. Yes, here image name in the YAML. Okay, so for example, here we are using the image name as AMD 64 CI. Yep. And developer will have to write this particular spec, particular utilities as per their application requirements. It can be different for, it can be similar for my API server too. Means this is just simple utility where we are just changing the image name and required parameters. Okay, so let's see the test. So as you can see on the screen, like a namespace default we have created, then image name is this, and it is showing the message such as like waiting for the pod state. So these messages are coming from the CITF, and you can see 2 dots here. So these 2 dots means Gingo has like executed 2 integration tests. Okay, so in the output also you can see that 2 tests have passed. Okay, now let us see this output in the explained format. So we have the CITF verbose log environment variable, which will actually set verbose log to true, and it will show us the debug output for the test. So this is the verbose log. You can see that what's happening inside the CITF, and yeah, this was the YAML file for the node disk manager which we had provided. Yep. So test have passed again, and you can see the verbose output here, a log from here. So we're starting the Minikube, and we have the node disk manager YAML file, then the status of the pod node disk manager, and it will just bring up the pod. It will start the controller, and it is showing the output for the LSBLK. Okay, by executing the command, and then we have the NDM device list inside the NDM pod, and then test have passed. So yeah, that is it. Any question till now?
So when you mentioned that it will check for whether the minikube is up and running, right? In one step. How does it check whether it's a minikube, or can I run this in G-Cloud?
Currently, we are only supporting minikube, but G-Cloud automation that we are still exploring the G-Cloud SDK right now.
If I have the kubectl installed, and then can I pass some environment variables of the existing cluster, so I don't have to?
You mean config you have to pass, right? So we haven't gone that.
How does it check whether minikube is installed or not?
We will just using simple system commands.
Kubectl get or minikube status?
Minikube status. Yeah. Setup. Yeah. So it's a common interface called as environments, which has like setup, status, and tear down. It can be used for different platforms such as Minikube, GKE. For the Minikube setup, yeah. So here, setup. Yep. So we are basically first checking the minikube status.
By checking minikube status, then we are calculating if we have to tear down it first, then restart, or just restart. Just start the content, the minikube. And,
okay. Then even before taking it to the minikube, for example, if I'm already having a GKE cluster and kubectl, I have a config. I just want to run the tests against that. That should be good enough for me.
Okay.
So as long as it does not require any extra step to execute kubectl command, it will be fine, because if we don't do environment or setup, if it is already been set up, then it's done.
Okay. So in this case, Indian operator is getting launched, right? If I give you the kubectl credentials, this test.
For those like who are writing the integration test, these are the resources. We have the documentation like for the CITF, which is nothing but a simple Go doc, and then we have the Gingo and Go Omega BDD style libraries. One is a matcher library, one is a testing library. Okay, so Go doc, like we have. Okay, so here you can see that all the documentation, you can find it here for all the APIs implemented in the CITF. Okay, so all right, that's it. My screen froze. Okay. Okay, thank you. Any questions on the? Thank you all.